We have been discussing spin echo as an example and trying to calculate explicitly the density operator evolution through the pulse sequence. So, we did that last time for a particular case of 2 spins with coupling and without coupling first and then with coupling later, and we had considered the spin echo sequence which was 90 degree x pulse followed by time tau, then a 180 degree x pulse followed by time tau, and then the evolution was calculated until this point. So, we are now going to make a slight variation in this sequence to see what difference does it make, whether the phase of the RF pulse does it make a difference, and if it does, in what way does it make a difference. So, that is a question we are going to ask, and therefore, we will simply change the phase of this pulse. Instead of a 180 degree x pulse, we will apply the pulse along the y axis and see what happens. So, as before, we will first consider 2 spins without coupling, which means the Hamiltonian is simply Hz, which is the Zeeman Hamiltonian. The evolution happens in the same manner here under the influence of the Zeeman Hamiltonian. Okay. Now, we have calculated explicitly the density operator in the previous case, and the difference here is only at this point. So, up till here the calculation is the same. Therefore, we will not repeat that calculation here, but simply take what was the density operator from the previous class at this point, and that is rho 3. Rho 3 is minus IKY minus inside bracket IKY cosine omega k tau minus IKX sin omega k tau, and then we have minus ILY cosine omega L tau minus ILX sin omega L tau. This was the result of chemical shift evolution from rho 2 to rho 3. Okay. So, and then the individual frequencies are here, omega k and omega L for the 2 spins. Now, the difference comes. We are now applying a pulse along the y axis and not along the x axis. So, what does it do? So, if it is along the y axis, this term does not change, this is invariant. So, this remains as IKY, whereas this one goes from IKX to minus IKX, and therefore, this becomes plus here. So, this becomes plus IKX sin omega k tau. Similarly, minus this ILY cosine omega L tau, and this becomes plus. So, plus ILX sin omega L tau. Now, put this again explicitly, you have it minus IKY cosine omega k tau and minus IKX sin omega k tau, and similarly here minus ILY cosine omega L tau minus ILX sin omega L tau. This is at time point 4. Next, we have to evolve under chemical shift once more for the next tau period. Now, there are 4 terms and each one of these has to be explicitly evolved. So, this is the first term IKY. So, this gives me here minus cosine omega k tau, and IKY evolves as under the chemical shift once more like this IKY cosine omega k tau minus IKX sin omega k tau, and the second term which involved IKX will give me this minus sin omega k tau, and inside bracket you have IKX cosine omega k tau plus IKY sin omega k tau. Similarly, for the L spin you have the same 2 type of terms minus cosine omega L tau multiplying ILY cosine omega L tau minus ILX sin omega L tau for the first term, and the second one here is minus sin omega L tau ILX cosine omega L tau plus ILY sin omega L tau. Now, we notice what happens here. So, rearrange the terms, this is minus cosine square omega k tau, okay, and then we have the other IKY term is here, and this is minus sin square omega k tau. IKY, if you put IKY, take IKY, take minus IKY, inside bracket you will have cosine square omega k tau plus sin square omega k tau, and so therefore what is in the bracket is is 1 and therefore you get a minus IKY. And what happens to this term? So, this is plus Ikx sin omega k tau cosine omega k tau, and here it is minus sin omega k tau cosine omega k tau, this will cancel. So, from these two we retain only this part, and now similarly if you see here we retain this part, these two terms will be remaining. This is cosine square omega L tau ILY and this is sin square omega L tau into ILY, and therefore these two terms will remain and we get ILY here and these two terms will cancel, and we therefore in the end for rho phi I get minus inside bracket IKY plus ILY. This is exactly equal to rho 2, right. So, therefore, what has happened, if you recall here, let us see what rho 2 in the previous class, minus IKY plus ILY, this is what we started off with. Okay. Now, in the previous class at rho phi we had here plus sign, it became rho phi is equal to plus IKY plus ILY. So, the effect of changing the phase of the 180 degree pulse is that this sign has changed and it has remained as rho 2, which is minus IKY plus ILY. The chemical shift is completely refocused, that effect is the same, there is no change in that one except that we have a change, the sign has now become minus instead of the plus in that case. This also we had seen in a vectorial picture when we discussed the spin echo earlier. So, this provides a mathematical rationale as to what is happening in the sequence. Okay. Now, let us consider the next case where you have two spins with coupling JKL. Now, we have Hz plus Hj, this is the Hamiltonian now. Now, we have seen before that the chemical shift is completely refocused at time point phi. So, therefore, we need not to calculate the chemical shift evolution once more here, because you remember we said evolution under Hz and Hj can be calculated independently. It does not matter which one we calculate first, which one we calculate second, it does not matter at all. Now, we assume that we have already calculated the chemical shift evolution under the chemical shift, the influence of the Zeeman Hamiltonian, therefore, we do not need to calculate that once more. We straight away take that result here, the rho phi was minus IKY plus minus inside bracket IKY plus ILY. Therefore, we start from there and now we calculate the evolution under the coupling Hamiltonian. So, this is the first term there gives me minus inside bracket IKY cosine 2 pi JKL tau. Why do I take 2 pi JKL tau now? Because I am evolving for the whole time period 2 tau. So, I did not evolve under the coupling before, therefore, I am now evolving for the whole period 2 tau. Therefore, I get here cosine 2 pi JKL tau minus 2 IKX ILZ sin 2 pi JKL tau. Similarly, the L frequency gives me ILY cosine 2 pi JKL tau minus 2 ILX IKZ sin 2 pi JKL tau. Here notice the difference is here you have IKS ILZ, here you have ILX IKZ. So, therefore, that was the simplest case, we could calculate the evolution under the coupling in a simplified manner. We do not need to calculate the coupling, the chemical shift evolution once more, we can assume that we have already calculated and we simply calculate the evolution under the coupling. The 180 pulse is applied to both the spins. Now, we consider the next case, which is case 2. Here the 180 degree pulse is applied only to the L spin. Notice the pulse sequence here, we have the L spin channel here and here is the K spin. Well, this is the K spin, however, this is the hard pulse which may be applied to both the channels. But to the L spin we apply only the 180 degree pulse. Though if you consider this as applying only to the K spin, then of course we have this, but if we are applying the first pulse to both the spins, then we will of course also will have a 90 degree pulse here when we say 180 pulse is applied only exclusively to this. So, we could in principle say that in this calculation we have calculated it assuming that we have applied the initial 90 degree pulse to both the spins. So, we can add that here. that so the first 90-degree pulse is applied to both the spins, therefore both are excited, and then we have the evolution going on under the influence of the coupling Hamiltonian. We could have done this experiment this way as well, in which case of course we apply the pulse only to the K spin. We need not calculate the evolution of the L spin magnetization here, because the L spin magnetization does not exist here. So if you have this pulse also, then we have generated both, then we can have the evolution of the L spin as well going on. So therefore both are correct, you can choose whichever way you want to do it. So here we have considered both the spins, and therefore we have said the rho 2 is minus IKY plus ILY. The first 90-degree pulse is applied to both the spins and on K and L, therefore we have this one now. Now what is rho 3? The rho 3 is minus the evolution now under the chemical shift. So minus IKY cosine omega k tau minus IKX sin omega k tau. This is the K spin evolution, and the L spin evolution gives me minus ILY cosine omega L tau minus ILX sin omega L tau. So put it, expand it and rearrange it properly, and we have rho 3 is minus IKY cosine omega k tau plus IKX sin omega k tau, and likewise minus ILY cosine omega L tau plus ILX sin omega L tau. So then now you see here there are 4 terms, right. This rho 3 has 4 terms. Now each one of them we will have to evolve under the coupling. So therefore rho 3 prime will now evolve under the coupling to rho 3 prime gives the result after the coupling evolution. So the first term here gives you this coefficient remains the same. So you have here IKY cosine pi j k L tau minus 2 IKX ILZ sin pi j k L tau. The second term gives me this coefficient is the same, sin omega k tau. We have IKX cosine pi j k L tau plus 2 IKY ILZ sin pi j k L tau. The third term gives you minus cosine omega L tau plus ILY cosine pi j k L tau minus 2 ILX IKZ sin pi j k L tau, and the fourth term gives you plus sin omega L tau ILX cosine pi j k L tau plus 2 ILY IKZ sin pi j k L tau. Okay. So therefore the result is now we have a total of 8 terms here. Let us rewrite this in a making some rearrangements. So the rho 4 is now after a 180 degree X pulse. Now that is after the on the L spin only. Okay. So rho 3 prime was after the coupling evolution, 8 terms are there, and now we apply 180 degree X pulse only on L. So therefore what happens? There is no pulse applied here. So this remains the same, this term remains the same, and here again IKX nothing happens to K spin, but the L spin 180 degree pulse is applied. So therefore this ILZ goes to minus ILZ, and therefore this becomes plus here. So this gives you 2 IKX ILZ sin pi j k L tau, that remains the same. So we put it in a different color for that reason. Now once again here nothing happens to this term, and on this term ILZ goes to minus ILZ, and therefore this gives me a minus sign here, minus 2 IKY ILZ. The third term, now this one ILY goes to minus ILY, because this is the X pulse, therefore ILY goes to minus ILY. So this is again in a different color, and whereas this one it is invariant, Lx is invariant, therefore nothing happens to this term, this remains as minus 2 ILX IKZ sin pi j k L tau. And in the fourth term this is ILX here, since this is the X pulse, this will be invariant, nothing happens to this, whereas this one the Ly goes to minus ILY, and therefore you get a minus sign here, you get minus 2 ILY IKZ sin pi j k L tau. Now therefore you rewrite this as 8 different terms, right. We have now 8 terms here, okay. Each one of them you expand it, you have 8 terms. Now what we do, each one of those 8 terms we have to evolve under the J coupling, because the J coupling is present during the next tau period. So, each one of those we now evolve. So, this is the first term. From there you get cosine omega k tau cosine pi j k L tau, and iky evolves as iky cosine pi j k L tau minus 2 ikx ilz sin pi j k L tau, and the second term gives me minus sin pi j k L tau cosine omega k tau, and this is the operator which we are evolving, and that gives me 2 ikx ilz cosine of pi j k L tau plus iky sin pi j k L tau. In these cases you should remember that summary of the evolutions which I had given earlier, because it is all what I am using here. Those summary equations which are there for the evolution under the coupling and evolution under chemical shift is what is being used. The third term gives you sin omega k tau cosine pi j k L tau, and it is the kx part which is evolving, ikx cosine pi j k L tau plus 2 iky ilz sin pi j k L tau. And the fourth term likewise gives me minus sin pi j k L tau sin omega k tau, and inside here is 2 iky ilz cosine pi j k L tau, and I get a minus sign here, minus ikx sin pi j k L tau. So, similarly the fifth term is cosine omega L tau cosine pi j k L tau ILY cosine pi j k L tau minus 2 ILX ikz sin pi j k L tau. The sixth term gives me sin pi j k L tau cosine omega L tau, then inside bracket you have 2 ILX ikz cosine pi j k L tau plus ILY sin pi j k L tau. The seventh term gives me sin omega L tau cosine pi j k L tau, and inside the bracket you have now ILX cosine pi j k L tau plus 2 ILY ikz sin pi j k L tau, and finally the last term gives you minus sin pi j k L tau sin omega L tau, and inside bracket you have 2 ILY ikz cosine pi j k L tau minus ILX sin pi j k L tau. This is at the end of J evolution from the after the 180 degree pulse. So, this is at just before the spin echo, at the time of the spin echo. Now, let us rearrange this and look at these terms which actually tend to cancel. Now, we notice here that earlier which I put it all in cyan color, and now I put the same in red color and say these terms cancel. Okay, this cancels with this. So, you have here plus, okay, and here it is a minus, and therefore this term cancels, this remains, and similarly here this term cancels with this term, 2 iky ilz term cancels with this 2 iky ilz term. The coefficients are here, you have the plus sin omega k tau cosine pi j k L tau and sin pi j k L tau. So, it is the same coefficients here with a minus sign, and therefore this cancels with this. Similarly, this term cancels with this term and this term cancels with this term. So, now therefore half of the terms are cancelled. So, let us pull together the other terms, and you have now the rho 5 is equal to minus cosine omega k tau cosine pi j k L tau iky cosine pi j k L tau, and minus sin pi j k L tau cosine omega k tau iky sin pi j k L tau plus sin omega k tau cosine pi j k L tau ikx pi cosine pi j k L tau, and minus sin pi j k L tau sin omega k tau minus ikx sin pi j k L tau plus cosine omega L tau cosine pi j k L tau ILY cosine pi j k L tau plus sin pi j k L tau cosine omega L tau, and here ILY sin pi j k L tau plus sin omega L tau cosine pi j k L tau ILX cosine pi j k L tau, and finally minus sin pi j k L tau sin omega L tau, and inside bracket minus ILX sin pi j k L tau. So, therefore, now you see we have the operator terms are either IKY, IKX or ILY, ILX, and then we have the various coefficients for those. So, now we pull together all those which belong to particular operators, and then you get this. So, here what we have is the coefficients of IKY. So, IKY is this operator which was there, and we pull together those terms which have IKY. So, here we have then minus cosine omega k tau IKY, and inside bracket we get cosine square pi j k L tau plus sin square pi j k L tau. Similarly for ikx, here you have the coefficient sin omega k tau and inside the bracket here cosine square pi j k L tau plus sin square pi j k L tau. Similarly for ILY, here you have cosine omega L tau and inside bracket here you have cosine square pi j k L tau plus sin square pi j k L tau. And then for ILX, you have the sin omega L tau and inside bracket here you have cosine square pi j k L tau plus sin square pi j k L tau. Now notice everything that is present inside the bracket is all 1, therefore it simply is simply equal to 1. Therefore I only have these terms remaining, right. So cosine omega k tau iky plus sin omega k tau ikx plus cosine omega L tau ILY plus sin omega L tau ILX. Now where is the coupling? Therefore the coupling is all vanished, right. All the terms which contain the coupling information have vanished. So therefore we say the J coupling evolution is refocused. In other words, this is called as spin decoupling. So if I apply a 180 degree pulse only on one of the spins, then it results in spin decoupling. Okay. So we can do this calculation for evolution with the initial 90 degree pulse applied to one spin only, then also we can do the same calculation. Okay. But since we have included both, it is actually more general. Now we notice one thing, in the previous case we after the row 4, that is after this point, we calculated the J evolution. So we switch the order of the evolutions. Earlier we were calculating the chemical shift evolution first and then the J evolution. Now we have done the J evolution and then we are going to do chemical shift evolution now. So after this term we will now do chemical shift evolution, because here I am demonstrating to you that you can actually switch the order of chemical shift evolution and coupling evolution, and that is what we have done here. So now after the row 5, I now calculate the chemical shift evolution. Chemical shift evolution gives me therefore cosine omega k tau, here iky cosine omega k tau minus ikx sin omega k tau. The second term gives me sin omega k tau ikx cosine omega k tau plus iky sin omega k tau, cosine omega L tau ILY cosine omega k tau minus ILX sin omega k tau, and finally sin omega L tau, and here inside ILX cosine omega k tau plus ILY sin omega k tau. So this is for the last tau period, this is after the 180 degree pulse we evolve for the next tau period under the influence of the chemical shift evolution. So now you see what happens, you look at the terms once more, rho 5 prime, this part we leave it as it is, but notice here there is a cancellation. So this term this is cosine omega L tau sin omega L tau ILX, this is plus sign here and a minus sign here, and this is sin omega L tau cosine omega L tau, this is the plus sign here, and these two terms will cancel. Because this is the chemical shift evolution of the L spin, therefore the L spin must have the omega L as the evolution. Okay. And then we can see that these terms will cancel, and what will happen to this? This is cosine omega L square omega square L tau. So what do you get? iky minus iky cosine square omega k tau, that is this, and this minus sign is multiplying everywhere, right. So iky cosine omega square tau minus ikx sin omega plus sin omega k tau ikx cosine omega k tau plus iky sin omega k tau. Therefore this is the plus sign, this is the minus sign here, I pull this together, I take minus iky, inside bracket I have cosine square omega k tau minus sin square omega k tau, and then you have this one here, this ikx sin omega k tau, okay, and cosine omega k tau, and this is sin omega k tau cosine omega k tau, these both have the same sign, this is minus minus plus and this is also plus. So therefore this gives me ikx sin 2 omega k tau. Okay. So similarly here the what we have here, cosine ILY cosine square omega L tau, and this is ILY sine square omega L tau, okay, because this is omega L tau here. And now inside bracket, therefore you will get cosine square omega L tau plus sine square omega L tau, that is 1, and therefore I simply written this as ILY. So therefore your rho phi prime is minus IKY cosine square omega k tau minus sine square omega k tau plus IKX sine 2 omega k tau plus ILY. So this is substantially simplified. Now what you have here? This is cosine 2 omega k tau. Therefore I have here minus IKY cosine 2 omega k tau plus IKX sine 2 omega k tau. So the k spin has evolved under the chemical shift, whereas the L spin chemical shift also is refocused. You do not see any term remaining here which contains omega L. Therefore, when I apply a 180 degree pulse only on the L spin chemical shift is refocused, but the K spin chemical shift continues to evolve for the whole period to tau. Therefore, I have here starting from my IKY, it was minus IKY, therefore I have the inside minus IKY cosine 2 omega k tau plus IKX sine 2 omega k tau. So, L chemical shift is refocused, whereas K spin chemical shift has evolved. So, therefore, in summary, we have seen the different ways of dealing with the spin echo. We have done explicit calculation under different conditions. When in the spin echo the 180 degree pulse is applied along the x or the y axis, what happens when there is only chemical shift evolution, what happens when the 180 pulse is applied on only one spin, that leads to spin decoupling. Okay, this is the common technique which is used in all multipulse experiments for decoupling during the course of the pulse sequence, particularly along the indirect detection periods in multidimensional NMR spectra. This we will discuss in greater detail, but we have demonstrated here the general principle as to how these things are working, and explicitly shown by density operator calculation the various terms that evolve under the influence of the different Hamiltonians.